Hello everyone, welcome back to this class. In last couple of classes, we have done with aircraft longitudinal stability and control, and here in this class we will discuss about the lateral stability and control. What are the parameters? What are the derivative is affecting in a lateral stability? What are the controls are there in the lateral stability uh, part that we will discuss. So, like in longitudinal case, when you have disturbed from the equilibrium position, it has a tendency to return to the original position that you called as a longitudinal stability. So, in similar case, if you disturb like this or like this, if it is returned to this original position, that will known as a that will be known as a lateral stability. Okay. And in next class we will talk about the directional stability when you give the disturbance in ya, and if it is tendency to return to the equilibrium position, that will be called as a directional stability. Okay. So in the longitudinal case, what was the control? Your elevator was the control, right? Now in this case, the aileron is a control. What is the job of the aileron? The job of the aileron to roll the aircraft, right? When you deflect the aileron in one side downward and one side upward, so basically what you are changing the camber of this wing, increasing the camber of this wing and decreasing the camber of this wing. So this wing will have a L plus delta L, and this wing will have a L minus delta L, and somewhere CG is here, right? So because of this net moment, you will roll the aircraft. Okay, this is lateral control. Okay, so now, but like longitudinal motion, the lateral is not a simple one that as compared to the longitudinal one, because here you will see the coupling. So aircraft has a plane of symmetry about y axis, right? But it is not having any symmetry about other two planes. So that means if you disturb one motion, automatically the other motion will happen. So this is nothing but the coupling. When you roll aircraft mein ya disturbance come and you start rolling the aircraft, then you will side slip also. Okay, you will start side slipping also, and one vertical force will act in that in direction. This has a some vertical distance about CG that will try to roll back. So as you can see, when your aircraft disturbed from the equilibrium position, it is side slipping and some force you are experiencing here, and it has some distance from the CG and trying to bring back to this original position. So that means this is the contribution of the vertical tail. So vertical tail is providing you the roll stability, right? It is trying to bring the original position, right? Okay. And similarly, wing also will provide the roll stability, and wing position also provide the roll stability. What kind of position you have? So one by one we will see. Okay. For example, if this is the case, and you have disturbed the aircraft from the equilibrium position. Okay. Now what will happen? You can see. Okay. This is very straight wing, and this is a some dihedral. So what angle it is making? The horizontal. If you do the projection, that is dihedral angle. Have you seen this type of what angle it is making with this horizontal? Okay, that is dihedral. Okay. Similarly, if it is down, it is anhedral. Okay. So this is the first case, and this is the second. So already I told when you disturb roll, it will start side slipping, right? And side slip what relative air makes with the plane of symmetry, I already explained to you, is known as a side slip angle. So somehow you have to kill this side slip, right? Rolling moment, it is induced, and you are an aircraft will try to kill the side slip angle, right? So like Cm alpha, you can write Cl beta here. Cl beta is a rolling moment. In that case, Cm was the pitching moment. So I write Cm. In that case, alpha I had written, and in this case beta. So this sign also what? Positive or negative? Negative. Because when you disturb from the equilibrium, it is side slipping, and now you are trying to kill the side slip by the inherent tendency of the aircraft. So that means Cl beta will be negative. Okay. So the graph will come like this. This is the case for stable, and this is the case of unstable. Okay. So case 1 is a stable case. Okay. But this you can achieve not only by wing, as I already told. The contribution will come from the wing, from the fuselage, from the vertical tail. Okay. So now first we will see the wing. Okay. For a wing, two cases I have considered. First case is just a straight wing, and second case is dihedral. Okay. Let's say you roll the aircraft either left direction or right direction. Okay. Maybe for example, like you have rolled the aircraft with dihedral angle. Okay. With phi angle, bank angle, you have rolled the aircraft. Okay. Tan gamma is Vn by V. V is sideward velocity. When you roll the aircraft, it will start side slipping, right? So at what velocity you are side slipping, that is V. Okay. And when you roll the aircraft, you will get one normal component of the air, right? That is Vn. Okay. So gamma is Vn by V. Okay. So you can write Vn equal to V gamma. Okay. And now how will you define this angle of attack? Let's say this is the case delta and delta alpha, normal component divided by forward velocity. And if this here also assume dihedral angle is small, so I can write gamma equal to Vn by V. And here if your delta alpha is small, I can write Vn by U. Okay. How will you define side slip? I already explained, right? Sin beta equal to sideward velocity divided by forward velocity. I am assuming I am writing everywhere U, right, here instead of capital V, right? So if your forward velocity is more than compared to the vertical velocity and sideward velocity, you may write under root U square plus V square plus W square is approximately U. Okay. So if beta is small, because here I am taking a small angle approximation, right? So beta, you have V by U. So now three angle I have. One gamma. Okay, you may note down this gamma Vn by V where written v is sideward velocity, right? Okay. Vn by v, this is first one, and then delta alpha equal to Vn by u and beta equal to v by u. Okay. If I substitute Vn from here to delta alpha equation, what you will write? You will write v by u gamma. Okay. And if v by u is side slip angle, so you can write beta gamma. Okay. So this, when you roll the aircraft, so let's say at this wing, this is delta alpha, and what will be the another case? It is going up, right? So the in that case it will be minus beta into gamma. Okay, so I am calling it say 1 everywhere, and now in second case for upgoing wing, delta alpha 2 equal to minus beta into gamma. So lift will increase, that will try to rotate the aircraft in a to equilibrium position, right? So that is how the wing is contributing. And if there is a no dihedral at all, so will the wing contribute? Only wing. I am not talking about the wing and fuselage together. No, right? So that is how you can comment on what will be the wing contribution towards the roll stability. Okay. You may note down this. So delta alpha, which is positive, this is for downwing, and delta alpha 2 minus beta into gamma, this is for upward upgoing wing. ओके, ऐसे किया आपने. अब जब इधर लिफ्ट ज्यादा होगी तो वापस तभी तो आओगे, and that is how you are mathematically coming. The aircraft is coming. Okay. Now, so one thing is clear: without dihedral angle, it is not possible to get any contribution from the wing towards the roll stability. Right? Okay. Consider the scenario. Three scenario. One is mid wing, another is low wing, okay. So this is high wing, this is mid wing, this is low wing. Among all three, what type of placement will provide roll stability? Okay. Consider the scenario. If you roll like this or like this, the air will accumulate here. Now, if you roll this, that will try to push you back. So that means from the common sense we can tell the high wing will contribute more towards the roll stability. Or if you want to draw the flow over a wing, you may draw like this. Okay, this is, let's say, high wing configuration. Okay, now the air is coming. Some another you can consider. Okay, So this type of flow you will get, right? So here increase in lift, here decrease in lift, and that is how you try to roll back. And if you consider the lower wing case, if you consider the lower wing case, okay, like this. So here you will have a when you roll the aircraft, here you will have a decrease in lift. Okay, here you will have an increase in lift. So which kind of tendency you will get here? Destabilizing, right? And here stabilizing case. Okay. So this is the contribution from the wing, right? No. And the contribution from wind wing is like, for example, you may comment that it will be the middle of high wing and not more stabilized case or not more destabilized case. Okay, middle of that. Okay, this is the wing contribution. Now we'll see contribution from tail. Okay, contribution from tail. Okay, now you can take this. Okay, roll, side slipping, one force is coming. Okay, I am drawing one force. I am saying as a LV because lift at a vertical surface. Okay, CG is somewhere below this line, right? Let's say CG. This distance I am calling as a ZV. Okay, and that is rolling in opposite direction, right? So I can write small l rolling moment, which is minus LV into ZV. That I can write. Okay. Y minus C. This axis system, right? X, Y, Z. This is positive X, this is positive Y, this is positive Z. So if you roll, if you translate in this direction positive, this direction positive, this direction positive. Similarly, for a roll, this is positive Y, right? Or this is Y, right? You take this hand like this and you curl. Where your thumb is pointing? Towards positive Y. That means this motion is positive. Similarly, for a ya, you take like hand like this, curl. So thumb is pointing positive Z. That means this motion is positive. Okay. Similarly, take on a x axis, take your hand like this and curl. Okay. Rotate. Where your thumb is pointing towards positive x axis, right? So this motion is positive. So what will be this motion? Negative. That is how I have put the sign negative. Okay. Now this you can write half rho v square s b cl, and this you can write half rho v square s v cl alpha of the vertical tail into alpha of the vertical tail. Okay, and alpha of the alpha v you can write, okay, angle of attack, which is beta only, right? So you can write cl here. You divide this minus half rho vt square divided by half rho v square SV, and this is force, and then into distance also, right? SV by S, ZV by B, and CL alpha of the vertical tail and beta. Okay. So in next slide you can write CL equal to minus eta V SV by S ZV by B CL alpha of a vertical tail, and then beta. You differentiate with respect to beta, you will get CL beta equal to minus eta V SV by S ZV by B CL alpha of the CL beta. You just differentiate, you will get. What is the sign of this expression? Negative, right? In a very simplistic manner, I have derived. I explain how this force is coming. You have some distance ZV, how you can write moment, and then you can non-dimensional this half rho square S into B, and then you can rearrange this, and finally you will get this expression, and if you differentiate with respect to the beta, you will get CL beta. Okay. Now consider this scenario. If you put this vertical tail up directly down, आपने नीचे कर दिया, तो साइन क्या हो जाएगा इसका? पॉजिटिव. तो वर्टिकल टेल डाउन करने पर वो स्टेबलाइज करेगा, डिस्टेबलाइज करेगा? डिस्टेबलाइज करेगा, राइट? सो इन एग्जाम द क्वेश्चन कैन कम लाइक दिस आल्सो. इफ यू पुट द वर्टिकल टेल below the horizontal tail, what will be the contribution you will get from the vertical tail? So answer is destabilize. Okay. So now this I have given you the contribution, what type of contribution you are getting from the vertical tail. Okay.